what you are thinking, right? So this is called the transfer characteristics. The other graph we saw, the ID/VD graph, that's called output characteristics. Okay, transfer characteristics is ID versus VG. Okay, ID/VD, the one that I showed you. This is the saturation region. This is the output characteristics. Okay, this is transfer characteristics. Okay, transfer characteristics, output characteristics. Okay, so with that, is this transfer or output? Transfer. Okay. So now, out of you can see there are A, B, C. There are 5 graphs, right? 5 lines, right? Yeah, 5 lines. Which one of them is showing the problem of punch through? A, B, C, D, or E? So which one has punch through effect? Which one has short channel effect? Question like that comes. Which one?
A.
Why?
Gate voltage is 0, so the current is very high.
Gate voltage is 0, is also current very high. It's not technically the correct reason. Because that one you can also tune the threshold voltage. The main reason is the gate voltage is not able to control so much. Right? The slope is very flat. That means the gate is not able to exert so much control over the channel. And of course, as Devan mentioned, current levels are high. Okay. So out of this, so you can see that the channel length is 1.2 micron. All that is provided over there. So which one is working nicely in a long channel region or in a long channel characteristics? Which one of them is performing? B, right? B with long channel 7.8 is the kind of characteristics that we are trying to make the A look like. Okay, so we're trying to make A look like B. Okay, because you can see wow, so many orders of magnitude I can control. Remember, this is logarithmic graph. Okay, I am able to control very, very nicely. Okay, so RP, as is mentioned over here, is the depth of the implant. So we can see if your RP is 0.3 micron, it looks like C. If RP is 0.5 micron, it looks like D. And if RP is 0.68 micron, it looks like E. So is D and E okay for us? D and E is okay, right? So it kind of looks like B. There's a lot of voltage control, etc. Okay. So what is wrong with C?
C is
too high what voltage? What do we call this? Too high threshold voltage, right? You need to apply much higher voltages to turn on. This is actually still pretty small, but with relative to B, which we are trying to emulate, this has a higher voltage. So if it has a higher voltage, what does that mean? Is it that means it's harder for me to? Is this an NMOS or a PMOS? First of all, is it an NMOS or PMOS? Why is it NMOS?
because positive.
Yeah, I'm getting I apply more and more positive voltage, more and more current is forming, right? So if this is getting higher and higher to turn on, it means it's harder for me to induce electrons or harder for me to induce holes. Harder for me to induce electrons, right? If it is harder for me to induce electrons, what is the problem that we're talking about? What is happening at that channel interface?
Very hard to form inversion
Because
there is the what's your dopant, your p-type dopant is blocking the channel from
no, it's not blocking the channel forming. The dopant density, the dopant depth, the depth at which it is inserted is shallower for C than compared to E and D. Remember, it's 0.5 micron or 0.68 micron. So when your doping is shallow, it is essentially means it's harder for me to accumulate the electrons. Because what type of doping is this? P-type or N-type doping? P-type doping. So in order to solve the punch through, okay, remember what is punch through? Punch through is this effect, right? Whereby which the depletion region of one and overlaps with the depletion region of the other. Why do I need a punch through? How does that solve the problem?
Higher dopant density than the wave decrease.
So this is the same problem as when we talk about PN junction, PN plus junction, P plus N plus junction, etc. Right? Originally it is P here. Let's say we had no depletion. Originally it was P here, N plus here. All the depletion is on the P type, P region. When I do a punch through implant, I am making it from P to a P plus illustratively. Okay, I am increasing the P concentration here. What does that mean? The depletion region will now shift, will become smaller. Okay, this kind of simple reason is why we started with diode, all that simple stuff. Because a P N plus region has a wider depletion region than a P plus N plus region, we put the implant. So the depletion region shrinks. But if that implant is too shallow, okay, instead of putting here, we are putting it close to the channel. Now the ability for us to form this electron channel over here gets affected. Because why? More boron over there. Harder for me to apply voltage to induce the channel. Okay, so we have to increase the concentration below so that the depletion regions don't overlap. But if the location is too shallow, then you start to affect the channel formation. Okay, so you guys should be able to. So again, right? Because I've been teaching this course for many years and I'm bored out of my mind. I will twist question here and there. I give you a graph, it may be NMOS, it may be PMOS, you may have to identify this, you may have to draw whatever kind of characteristic. So don't just look at the question like this, twist it around in your mind. How would the graph look like if it was an NMOS device? Okay? If I just provide you an IDDG graph and I ask you to identify what is the dopant in the source or the drain, you should be able to do it. What type of material am I using for punch through implant? You should be able to identify it. Okay, because they are all interlinked, right? It is because I am trying to form an electron channel over here, I need a P-type doping. If I was making a P channel over there, that means my source and the drain would be P plus, right? That means I would have to be depositing an N-type dopant over here, right? And if let's say I provide you 3 implant energies, you should be able to say which implant energy would be better, which implant energy would be worse, right? Because from 3012, you know that the depth of the implant depends on the energy that you are shooting it with, right? If it is too low energy, too shallow implant, not good for our transistor. Okay, so this is integration. So you need to understand all the concept, right from the device characteristics all the way to the actual process of forming this. You will discuss among yourselves, flip it around, NMOS, PMOS, option, etc. All that discuss right now with your colleagues. Discuss, talk.
It's just the like, it gets on top of it.